Okay, well, thanks, Christian, for accepting this invitation. It's nice to see you again. And, well, go for it.
Okay. Well, thanks for the invitation. I would rather be in Charlottesville, but than in my basement, but that's how it goes. All right. So I'm going to talk about some essentially finished work, or at least some version of it is done. Okay, and I'm working at the National Science Foundation at the moment, so I have to put this disclaimer here that nothing I will say about cohomology will be represent the view of the National Science Foundation or the US government. So any views of cohomology are my own. All right. Good. So I'm going to talk about something that hopefully should be of some interest to you, sort of fairly within the domain of your seminar. And it's something I've been thinking about several years, and now I have a somewhat different view of things, a more algebraic view that might be the taste of the operator algebraists among you. Okay, so let me start out with some introductory comments about Banach modules and introduce cohomology of this. Okay. So this is about discrete groups acting on Banach spaces linearly or affinely. Okay, most often these will be isometric actions, but this is not really needed here. So okay, so what is it? So we start out with a countable discrete group. The fact that it's countable or discrete is not so important. You can certainly generalize this to, say, local compact groups or other types of groups. But I'll just stick to the discrete realm. So a Banach module, a Banach G-module, is really a pair where I fix a Banach space and an action of this group G by linear automorphisms of X, and I ask that this is continuous. So of course G is discrete, so this means just that this is by bounded linear automorphisms of X. Now you could think about real or complex spaces, but for what I'm gonna do here, I'll just focus on real spaces. This is not so important. You can make changes as needed. Okay, and again, if the module action is by linear isometries, I'll say that this is an isometric Banach G-module. Okay, this might be a Hilbert space, or it might be a more general Banach space, say LP, or things that are just defined geometrically, so uniformly convex or reflexive spaces or something of that sort. Okay, so once you fix such a module action, you have a standard Cochain complex associated with this. So this is just a sequence of linear spaces, C0 of Gx, C1 of Gx, etc., and with some operators between them. Okay, so what is this C to the n of Gx? Well, this is just the vector space of all maps from the finite product G times G, etc., G to the power n into X. Okay, so this is easy. Of course, this is a vector space if you in the vector X here. Okay, so in other words, C to the Cn Gx, this is just a product of copies of G, a countable product of copies of G, of X. And So being a countable product of Banach spaces, it's a Fréchet space itself. It's not a Banach space, it's just a topological vector space, but a fairly nice one. All right, so just a word about the extreme case. In the first, for 0, you only have one element here, so you can identify C0 GX just with one copy of X, so this is just X itself. All right, and so I'll refer to the elements of this as n cochains, or cochains in general, but if you want to be specific, you say these are n cochains. Okay, so this is easy enough. Okay, so I've got just elements of X in the first copy. These are maps from G to X in the second copy, maps from G times G into X, etc. All right, and you now define the co-boundary homomorphisms in this cochain complexes. And this is a somewhat complicated formula. So if you're not familiar with it, you're not going to remember this formula. This is a somewhat complicated expression that I'm not going to be able to give you much insight into right now. But let's just look at the first couple of cases. Okay, so recalling that the first space in this complex is just X itself. You let this operator D1, it acts on X. It gives you, so it acts on a single element of X, and it gives you a function of one variable on G. Okay, and that variable enters by the linear action pi, and so I apply pi to G1, and I apply this to X, and then I take the difference with X. This is what the first formula gives. And for the second one, so I start out with a function phi, which is a function of a single group variable, and it outputs a function of two group variables, and this is the expression here. So pi G1, phi of G2, plus pi of G1, minus phi of G1, G2, so the product of the two elements. All right. Now, so for cochain complexes, of course, the main defining property is that the composition of two of these operators in the right order gives you 0. Okay? So in other words, the image of D1 is contained in the kernel of the next one. And so the associated cohomology of the module, the nth cohomology, is a quotient between two spaces. The first one is the vector space of CoCycle, so that's the kernel of dn+1, and it's quotiented out by the subspace of co-boundaries, which is the image of the prior operator. Okay, so you are checking essentially the to which extent this sequence of operators is exact. Okay, the failure of exactness at each term. Okay, this is the cohomology. Okay, so let's look at the one cohomology, because this has a concrete interpretation that is perhaps this is the main interest underlying sort of work in this area. Okay, so let's remember that the first operator D1, when I apply it to a single vector in my space, I get a function of one variable on the group given by this expression here. Okay, so Z0 of Gx, this is by definition the kernel of the first operator. Okay, so it's the set of x's in X, so that this delta 1 of X is always 0. So it's just the set of x's so that pi g of X is always equal to X. So in other words, Z0 is just the space of G invariant vectors in the module. All right. Similarly, if you look at the expression for D2, the space Z1 of G of X consists of all maps going from G into X, which satisfies the following CoCycle condition here. Okay, it's a set of all maps so that phi, all maps phi, so that phi of G times F can be written out as pi G applied to phi of F, and then plus phi G. Okay. Now, okay, so that's the view of these one CoCycles. Okay, now if you think about what is a fine automorphism of a Banach space, okay, this is a continuous affine automorphism. This is a map that can always uniquely be written as, so I've got this curly A, so this map is just a linear map, A plus a translation. Okay, so I've got a bounded linear automorphism of X and a vector that I'm translating with. Okay, so that means that if I have a group that's acting by continuous affine automorphisms on a Banach space, this corresponds exactly to a pair of, so I'll write alpha equals pi and phi, okay, where pi is just an action by linear automorphisms of the group on the Banach space. And then phi is the translation part. So phi of a group element G associates to G the translation part of the corresponding affine automorphism. And if you just look at the composition of two affine automorphisms, you find that this phi, this translation part, has to satisfy this CoCycle equation. And this is just what comes out of it. So that means that if I fix a Banach module, okay, so I have a fixed group and a fixed linear action on this on a Banach space, then you get a bijective correspondence between the space of one CoCycles associated to the Banach module and the class of all continuous affine actions of G on X, whose linear part is always this module action pi. Okay, so fixing the module action, then you get varying, then CoCycles are just different affine actions that correspond to these CoCycles. Okay, and that correspondence is that you take a CoCycle and you just associate it to, you use that CoCycle to twist the linear action, the module action that you get out of it. Okay, so this is a bijective correspondence. And the co-boundaries, okay, so this is the image of delta 1. These are those where the CoCycle is given by this specific expression here, pi g applied to x minus x. These are exactly the affine action. Oh, sorry, I should say they correspond to the affine action where you have, or they correspond to linear actions where you've just moved the origin to x instead. Okay, so you you have the same linear action. It's an affine action, but which is where I've really shifted the origin from 0 to x instead. Okay, so these are, so in other words, if you look at the cohomology, this measures the complexity of the collection of all affine actions with linear part pi. So all affine actions of G on X, where I always have the linear part fixed, modulo those that have that fix a vector in X or fix a point in X. Okay, so that's one way of measuring the cohomology. Okay, so for example, the cohomology is 0 if all affine actions fix a point in X. So if I fix the module action, then all affine actions with that specific linear part have a fixed point if and only if the cohomology is reduces to 0. All right, so this also means that the first cohomology can be approached either geometrically through the study of affine actions, where you use geometric methods, or you can approach it purely algebraically. And what I'm going to do, present to you today, this is a purely algebraic approach to it that simplifies many of the geometric arguments and give you significantly stronger results in certain cases. Okay, so let me just say fixed notation for group algebra. Okay, so I start out with a discrete group, and then I associate it to it the real group algebra. So what is this? This is just the vector space of all formal, finite formal linear combinations of elements of G. Okay. And another way of saying this is that such an element C in the group algebra, you can just view it as a finitely supported function, real valued function on G. Okay, and so of course with this identification you can equip the group algebra with the convolution product that makes the group algebra into an algebra. All right. So in this group algebra, I have a specific subset, namely the group simplex, which is the set of all convex combinations of the elements of G. Okay, so this is the convex hull of the Dirac functions in the group algebra. Okay, so in other words, it's the positive elements of mean 1. Okay, and just one word here, namely that if I start out with the Banach G-module, okay, then of course this this module action, which is a linear action of G on X, of course I can see it just as a homomorphism or group homomorphism into the algebra of linear operators on X, and this extends canonically to a representation of the R algebra, so that I won't make a difference between these. Okay. Now, so the first thing I'll do is I'll talk about how you can get complementation of one cohomology. Okay, so suppose you have a finite generating set for a group G, and you have an isometric Banach G-module. So in other words, the Gx by linear isometries on X. Then the module, or just X, is said to have almost invariant unit vectors. If for any epsilon, I can find a unit vector that's invariant up to epsilon by all these generators of the group, these finitely many generators of the group. Okay, so in other words, pi of G moves X less than epsilon. Okay, now if I start out with now a uniformly convex isometric Banach G-module, so assuming that the Banach space itself is uniformly convex, then I have an equivalence of two facts, namely, okay, if X does not have almost invariant unit vectors, so there's a spectral gap here, that's if and only if the operator I minus pi of psi is invertible, where psi is the average of the generators. Okay, so I take the sum of the generators, I divide out by the cardinality, so I just take the average. This gives me an element in the group simplex. Okay, and I apply my pi to it because pi extends to the group algebra. Okay, and then that operator is invertible if and only if you don't have almost invariant unit vectors. Okay. This uses the uniform convexity of the Banach module. This is fairly straightforward to see. All right. So this operator is going to come up again and again. So this is why we need this basic fact. Okay, so now if I've fixed my psi to be this average of the generators, I can now define a sort of a weighted average operator on that goes from C1 to X by, okay, so R psi applied to a function of on G with an X-valued function on G is just, well, I evaluate phi on all of the elements of G, and then I multiply with these with this psi, the value there. So this is sort of a weighted average. Okay. And the main thing about this is that if I now compose this D1 with arc psi, you can write it out, and you will see that in fact you get nothing but this I minus pi psi. Okay. So in other words, this operator that I just described when it was invertible, it always factors through C1 of G. Okay, so it's an operator between X and X that factors through my space of cochains via the D1 and this R psi. Okay, that's just what is described above. Okay, so in particular, if I minus pi psi is invertible, then you can define an idempotent operator on C1 in the following way. Well, first of all, it will have image equal to the space of co-boundaries. So it really maps C1 into the space of co-boundaries, or onto the space of co-boundaries. And what's the definition? Well, remember that this middle operator here is the inverse of I minus pi psi is exactly the inverse of the composition of R psi with the D1. Okay, so that gives you the idempotence of these P sub psi. Okay. And so this straightforward computation here gives a direct and instructive proof of a strengthening of a result of Piotr Nowak, who had some more complicated computation here. Namely, that if I start out with a uniformly convex isometric Banach G-module without almost invariant vectors, unit vectors. Okay? Then, first of all, this inverse here exists. Okay, that was the that was equivalent to having almost not having almost invariant unit vectors. Okay? And then in fact I get a decomposition of the space of cochains into my space of co-boundaries plus a canonical complement of this space. So this is a vector. This is a topological vector space decomposition. Okay? Because all these operators are continuous, and I'm talking about Fréchet spaces. Once you direct sums still behave nicely. Okay, so in other words, the complement here is nicely describable. Okay, I know exactly what they are. These are the cochains whose weighted average is 0. Okay, where the weighted average is over this this sum of generators. Okay. Good. So that's the and in this case therefore you also get the decomposition of so this is a decomposition of the cochains. The CoCycle is a subspace that lies in between B1 and C1, and therefore you get a similar decomposition of that superspace of B1, okay, where you just restrict it. All right. Now, the goal is to extend such a result to from one cohomology and to get an information about cohomologies at higher levels. And so the first thing one has to do is to extend the cohomology computations. Okay, so remember, so I start out with G acting on X. I view this as a map from G into L of X, and therefore I just extend it linearly to the group algebra. Okay. Similarly, if I start out with a cochain, which is a map from G cross G cross G, etc., mapping into X, this has a canonical unique extension to an n multilinear map from the nth power of the group algebra. Okay, so the group algebra times the group algebra, etc., into X. Now, unfortunately, this extension is more than you really want to look at, because you are not really getting multilinear maps. You're getting something less. Okay, so I'll just restrict that extension to a little bit smaller space. Namely, I'll look at the group simplex times the group simplex, etc. Okay, so n product of n copies of the group simplex, and then I extend, or I take the restriction of this full extension to the n multi-affine map from the nth power of the group simplex into X itself. Okay, and then I'll let Cn of delta G of X denote the collection of these extensions. This is in fact just the same as the collection of all n multi-affine maps defined in that from delta of G, etc., into X. All right. Okay, and once you have the space of cochains on the group simplex, you can define the co-boundary maps simply by using the same formula as before. It makes perfect sense now. Okay, and because of the various properties, sort of a lengthy computation, or a straightforward but lengthy computation, shows that actually it does nothing than what you had before. In other words, so I have an isomorphism between the space of cochains on G and the space of cochains on delta of G. Okay, that's just the extension to multi-affine maps. And this whole diagram commutes. Okay. That means that, first of all, you don't have to distinguish between phi and the multi-affine extension, so you can just apply all computations directly. And for example, this concrete operator, this weighted average operator that I used before in order to decompose, to show the decomposition of the space of one cochains. If you rewrite it, you can just see that R psi of phi, this is just, you apply phi, or rather the in multi-affine extension of phi to the element psi, and then you just change the sign. Okay. And with this, you can get a simple algebraic proof of a result of a previous result of Bader-Furman-Gelander-Monod, which states the following. So they were really interested in lattices in Lie groups, but there's a general fact here, namely, so you take two finitely generated groups, G and F, and then you look at a uniformly convex Banach G times F module. So you have two commuting module actions of G and F separately on X, and assume it has no almost invariant unit vectors. Okay, the combined, the G times F action. Okay. You also assume that separately there are no vectors that are of X that are invariant on all of the elements of G, and there are no non-zero vectors invariant under all the elements of G, and no non-zero vectors invariant under all the elements of F. Okay, this is weaker than claiming that there are no almost invariant unit vectors. Okay, so neither G nor F acts trivially on any part of F, on X, and G times F have no almost invariant unit vectors. Then you get that the whole first cohomology reduces to zero. So in other words, any affine isometric action, sorry, I should have said this is a uniformly convex isometric Banach G-module. Okay, so any isometric affine action with this specific module action as a linear part has a fixed point. Okay, so let me see if I can give you a brief idea of what is going on here, because the main ideas are fairly simple. Okay, so by the assumptions of not having fixed points or almost fixed points, you can find xi in the group simplex of G, as zeta in the group simplex of F, so that I minus pi applied to the product of the two is invertible. And neither of the two, of pi of xi and pi of zeta have non-zero fixed points. Okay, so then you go back and use the direct sum decomposition of now Z1 of the space of cocycles. Okay, so you get the space of cocycles splits up as a direct sum between the space of cochains and then this particular complement. Okay. And what I wanted to show was that the cohomology here is zero. That's the same as saying that this quotient is zero. So in other words, what I have to show is that this part, this complement, is 0. Okay. So in other words, I have to show that whenever I have a CoCycle that takes the value 0 on this product, then it's actually constantly 0. And now you just use some easy computations. I have a CoCycle that takes the value 0 on this product. So I start out writing this down. Well, I have the CoCycle equation for this product here. I write it out. Okay. But these two, psi and zeta, one belong to delta of G, the other one belong to delta of F. G and F commute, okay, because it's a direct product of the two. So I can write zeta and psi in the other order, and then I can write out the CoCycle equation once again. And then computing, you find that actually phi of psi is fixed by pi psi zeta, but this operator was invertible, so the only thing that's fixed by this must be 0. And you do a similar argument, and you get that actually phi is 0 on absolutely everything. Okay, so I'll spare you the details of this. Okay, so this is a very simple proof of a theorem that used sort of geometric tools prior. It uses the existence of minimal closed convex invariant sets for various parts of the action. So it's a very geometric proof. Here you get just as a consequence of this decomposition that was looked at initially by Nowak. Okay. Now the main thing I want, sort of the main result coming out here is split exactness of Cochain complexes. Okay, so suppose you have now two groups and two Banach modules, X and Y for G and F. Okay, so then a Cochain map. So I've got this two standard Cochain complexes that I wrote out. This is a sequence of continuous linear operators between the terms in the Cochain complex, so that you get a commutative diagram. Okay, so I write out the Cochain complex for the first module, I write out the Cochain complex for the second module, and then I just want linear operators or continuous linear operators between these Fréchet spaces. So to make this that commute with the boundary homomorphisms. Okay, and because T commutes with the boundary homomorphisms, or this sequence of linear operators commute here with these D's, you get that T induces a map on cohomology. Okay, there's a well-defined map of the cohomology, the sequence of cohomologies into the sequence of cohomologies of the other one. Okay, so those are Cochain maps, and so the Cochain map is null homotopic if I can find continuous linear operators. Now these are not these are between the terms, but they don't preserve the order or the degree. They decrease the degree here by 1, so that you get this expression. Okay, so, and I just start out with the 0 map. R0 and D0 are the 0 maps. So in other words, I get a diagram here. Sorry, these S's, forget about these. It's from So I get the diagram, but it's not the commutative diagram. I get some more complicated expression. Okay, so the main fact about the being null homotopic is that the null homotopic chain map will induce the zero map on cohomology. Okay, so T, it's a chain map, so it induces a map between the cohomologies of the G module and the cohomology of the F module. And being null homotopic implies that this will in fact be zero. Okay, it will map everything to zero. All right. Okay. Now, so if I have a group G and I look at the group algebra, I can of course look at the commutant of G in the group algebra. It's straightforward to check that this will be the what are the commutants are exactly is spanned by the averages of finite conjugacy classes in G. So in other words, I take a finite conjugate, a finite conjugacy class in G, take the sum of the elements. Okay, that gives me an element in the group algebra, and I span the span of that is exactly the commutant. Okay, so I have an expression for this commutant. Okay, and so the main proposition, underlying proposition here is that, okay, I start out with a group and a Banach module, and I pick a psi in the group simplex which lies in the commutant of G. Okay, so it commutes with everything in G. Okay, then the Cochain map that takes, so it operates on all levels of cocycles, takes a phi, on all cochains. Okay, so it takes any cochain and takes it to the composition of that cochain with the operator on X I minus pi psi. This cochain map is null homotopic. Okay. So, in fact, so what are the witnessing operators here? So remember, I have to produce, so I have this T that just takes a cochain, okay, goes from the same module to the same module, or from one module to the same module, and it just takes a cochain and composes it with an operator, post-composes it with an operator on X. Okay, so I have to find these R0, R1, R2, etc. Okay, and what are these operators? Well, they have this specific expression. They insert, they take sort of an alternating sum of inserting psi in the particular places in the Cochain. Okay, and in fact, if you look at it, the first operator, so the R1, the first non-zero operator, is just exactly this R psi that we looked at before, that came up in this decomposition of one cohomology. All right, so that's the main underlying proposition here. Okay, and what's the impacts of this? Well, let's see here. So I fix a group and a Banach G-module, then I have an equivalence between a few different properties. Okay, so I have the cochain identity map. Okay, so it goes from one cochain complex to itself. It just maps, it's the identity on all terms. This being null homotopic is equivalent to there being an invertible null homotopic cochain map. That may not be too surprising, But if you look at what it says, this is actually equivalent to the whole Cochain complex being split exact. Okay? So in other words, exactness means, well, that the image of this operator here equals the kernel of the next one for all terms. Okay, so that means exactly that. So exactness is just that all the cohomologies are 0. And split exactness means that, well, not only that, actually the co-boundaries equals the CoCycles, and that space is complemented in the space of cochains. Okay? Not just at the first level, but at all levels. Okay, so this is obviously the nicest possible situation, the nicest possible cochain complex you might have, perhaps also the least interesting, but it means that there's really nothing to be gained from this. Okay, so that means that, okay, so going back here, I knew that if I picked psi in this commutant, this cochain map is non-homotopic. Okay. And so if I can find a psi that lies in the commutant, so that not only, so that this operator on X now is invertible, then the corresponding cochain map, well, it's null homotopic. That was the assumption that psi was lying in the commutant, but it's also invertible because obviously this operator is invertible. The post-composition with this invertible operator is always invertible. Okay, and that would be enough to get split exactness of the whole cochain complex. And so for that purpose, so let's remember that the commutant was the span of the averages of the finite conjugacy classes. So let's, if I fix a group, I let phi, capital Phi here, denote the subgroup of G consisting of elements with finite conjugacy class. And this is a normal subgroup of G called the FC center. Okay. And so now I have, I can put things together. And so I start out with a group. Okay, I should say, and an isometric Banach G-module, so that X does not have almost phi invariant unit vectors. Okay, so the action by the FC center does not have almost phi invariant unit vectors. Well, then the whole cochain complex is split exact. Okay, and so in particular, the whole cohomology, or all cohomologies vanish. Okay, and I've sort of set it up in the simplest situation where you don't have to talk about different groups, but obviously they're much more refined consequences that you can talk about here that gives you under weaker assumptions. So the problem is that if you have a group here where maybe the FC center is not so large, then this is not so interesting. Okay, so for example, if you have, well, to take an even simpler example here, suppose you have a group with finite conjugacy classes that acts on an isometric Banach module without almost invariant vectors, then the cochain complex is split exact. All right, so thanks, and I appreciate your suffering.
Thanks, Christian. Thanks for the nice talk. Do we have any questions for Christian? Oh, David's already saying he has.
Oh, sorry.
Wait, I'm confused. Are you guys raising the hand to ask questions? Or no?
Ben is.
Oh, okay, so go, Ben. I thought David was as well. Sorry.
Yeah, I guess I have several questions, but I'll just keep it to one. So, for example, in this last theorem, like if you had a non-amenable FC center, this gives you like a strong version of vanishing first L2 Buddy numbers, or for all the L2 Buddy numbers. So this kind of reminds me of this result of Robin Tucker Job that like if you take an interamenable group, then it has vanishing first L2 Buddy number. Do you know if there's sort of applications along these lines to sort of other like higher L2 Buddy numbers of other groups, beyond just non-amenable FC center or something like this?
No, I haven't. So I haven't thought about L2 Betty numbers. So the short answer is no. But now I want to look at it. I mean, the main thing I was interested in here is not when you're looking at the FC center. It's rather when you have you're looking at, rather than looking at you really want to take you start out with the cohomology of the whole group, and then you take the restriction to a subgroup, and then you want to say that this restriction map is 0. So those were the lines that I've been thinking about. So this is where you have G can be written as a product between a subgroup and a group which has finite conjugacy classes with respect to the other subgroup. So it's more flexible than just talking about the FC center. Okay, but I wanted to keep it simple here.
Sure.
I should look at that.
Can you other things about like sort of, I think similar to what you're talking about, like an intermutable pair or something like that?
Yeah.
That sounds vaguely similar without actually, reading the paper.
Yeah. Okay, I'll look at see what he's done about.
What else? More questions for Christian?
I mean, I can go again. Sorry.
I think Ben should ask questions. Ben is going to have the best questions out of all of us by far.
I made a horrible boo-boo there. I can ask another question.
I'm serious. Go ahead.
No, anyway, whatever. Yeah, so I guess this like was Bader-Furman-Monod, Galander. Did I get all the names?
Bader-Furman-Gelander-Monod.
Oh, wow, he's got all the names. So yeah, I briefly looked at it and I guess what they're trying to do sort of property T generalizations to like Lie groups or something. Do you get like a higher dimensional version of that? With your
Yes.
Oh, okay,
So,
great.
Yeah, I mean, so their paper. This is this paper in ACTA 15 years ago, something of the sort. Their goal was to rather than study property T, then study more general modules. Instead of just Hilbert modules, look at more general Banach modules. Okay, uniformly convex. I had a paper with Bader and Sauer on reflexive Banach modules. Okay, so this is really about property T, but more general, for more general modules rather than just. So there are two. I mean, okay. The thing is that when you have a Hilbert space, then you can do spectral theory, and that's how many of these things go about. Here, there's no spectral theory because I mean, if you're working with an LP module, yes, maybe you know what operators look like and maybe you can do something. Here, you just have an operator on maybe a reflexive space or uniformly convex, so you can't say anything. But on the other hand, you think differently, and I mean, it's certainly given me good ideas to get away from this the spectral perspective on these things. So this is sort of the direction that it goes in here.
Great, thanks.
Okay, I have a random question though. In what is it? Something like equivariant geometry of Banach spaces or something. One of your papers, you have a paper named something like this, right? In Forum Mathematica Sigma, I think, that you pretty much look at the first level of those things a lot, right?
Yes.
But you have your goal is to get applications to the nonlinear geometry of Banach spaces there. And well, my question is if you are also thinking about nonlinear geometry of Banach spaces in these higher things.
Well, so the thing is, so there the goal was to you start with some embedding which is not algebraic in any way. It just has some geometric properties. Okay, between two Banach spaces. I mean, Bage, you know the paper, I know. And then you apply amenability of the Banach space to get something better. You raise the map to become a CoCycle, a one CoCycle. That's really, you do some averaging and then you get the one CoCycle, and then well, it has some nicer properties, some algebraic properties, and they have also some nicer geometric properties. I mean, now if you go up to higher cohomologies, I really don't know how you would interpret this. Okay, so your group would be a Banach space. So you have a Banach space that's acting on another Banach space, or rather itself. And then, yeah, I don't know. Maybe it will say something about maps from X cross X into Y.
Mm-hmm. Okay. Okay, well, thank you. Do you have more questions?
I think I just need to think some more. But yeah, maybe the rest can be done over like email or something. But, yeah.
Okay, then, well, thank you again. I'm going to stop the recording now then.